Okay, I'm recording this video for my MAE 3033 Machines and Mechanisms class at Oklahoma State University. In our last class period, we started the discussion on dyad synthesis, and we talked about what dyad synthesis meant for a four-bar mechanism, especially moving through three positions for rigid body motion. We're now ready to start writing the equations that we're going to use to describe and solve for the machine that will give us the motion that we want. And the theory is explained nicely in a textbook called Mechanism Design by Erdmann and Sandor, in a chapter called Synthesis, and a section called Dyad Synthesis. And the key figure that leads us to the theory and the equations we're going to be solving is figure 8.59. And I have had great difficulty through many years getting everybody to understand what this figure means. And so this is my latest and greatest attempt at explaining what this figure means and the resulting equation that flows from it. And I'm doing this using MathCAD plotting of a 4-bar. So here we go. This is the figure from the textbook. It shows a 4-bar mechanism, which is a grounded link with a grounded pin joint here, a grounded pin joint here, two links connected to the grounded pin joints also connect to this triangular plate called a coupler link, because it couples the left side of the 4-bar mechanism to the right side of the 4-bar mechanism. The coupler plate could have any shape desired. It could simply be another straight link. In this case, we've made the coupler link into the shape of a triangle to indicate that it may have more sophisticated shape. Now, to explain, this picture is basically an attempt to visualize this machine moving from one place to another. On a static piece of paper, it's hard to demonstrate a machine moving from one place to another, so that's what I'm going to try to do in the MathCAD. And so I've got some things set up to allow me to make the machine move. And so I'm going to move that one down into position, move and slide this back to the 0 spot. See if I've got control of motion. I do not. Let's move all of these others. Give me just a second. Got to move some other things up. Now I've got control of the motion. Okay, so what I've attempted to do is make this drawing of a 4-bar mechanism over here look a fair amount like the one over here. And so where I have a link pinned to ground running roughly vertical, I have a link with a roughly looking grounded pin joint running vertical. I have a link here running mostly to the right and a little bit up. I have that same link pinned to ground here running to the right and moving mostly up. And connecting those two links is a coupler link. Well, I've got the coupler link right now shown as only a straight line coupler link drawn in heavy green, so that the heavy green represents what I would call the core piece of the 4-bar. Now, where is the triangular plate? Well, this yellow line and this red line right now, okay, are the equivalent of the triangular plate. Notice point P1 here and P1 labeled there. So this left-hand thing is a crude representation of what's in this picture. Now, what we're trying to represent in this picture is this 4-bar mechanism moving from a point where this point on the triangle is hitting point P1 to a point where the triangle point is hitting a different point, but they're not showing the entire mechanism. So let me first of all sort of demonstrate the linkage moving by moving a slider, and we can see that the 4-bar has moved a little bit. And now, where's the triangle? The triangle in its initial position, let's go back to the initial position, is right here. Green line, yellow line, red line. And that triangle is a rigid body. This airfoil, and we talked about moving an airfoil flap in class last time. This airfoil is a rigid body that is welded to the triangle. So the triangle and the airfoil together are one rigid body, and so I would say the triangle and the airfoil are together the coupler link rigid body. Coupler lengths might be a straight line, but coupler lengths may have the shape of triangles welded to airfoils. Now, I'm going to move this just a little bit into a new position. Let's move it far enough. Here's the original 4-bar. Can you envision that? It has moved. Here's the original triangle. It has moved. Here is the 4-bar in the new position. Easy to see. Here's the triangle in the new position. Easy to see. What I hope you can recognize is that this blue airfoil has moved with the triangle, first of all, as a rigid body. They are all one rigid body. And now let me move. And so the 4-bar can move and move and move. And the triangle and the airfoil are moving as a rigid body with it until we get to some extreme position. I'm not really interested in the extreme positions. Instead, let's go back to the beginning. Okay, what I want to do is move from a position that I would call position 1. Now let's describe some terminology. In this picture, there is a vector superimposed on this left-hand grounded link, which I would tend to call the input link of a 4-bar. This vector has the name W sub A, and we're going to call the left-hand side of this mechanism the A side of the mechanism, governed by point A0 and A. The right-hand side of this mechanism we're going to call the B side of the mechanism, and we have a grounded point B0 and a moving point, a pin joint B. And so on the left-hand side, a vector superimposed between A0 and A is called WA. On the right-hand side, there's another vector not shown that connects B0 to B, and we're going to call that one WB. Okay, I'm not going to really worry about left hand, right hand at this point. I'm going to simply say, okay, we're going to call this the W link. Now, on the coupler, rigidly attached to the coupler, is a vector that goes from A to a point labeled P1. And if you remember from our discussion last time, key points in a synthesis problem would be having a P1, a P2, and a P3 for 3-position synthesis. So here's the P1 in this figure, there's the P1 in this figure, and that's where the airfoil connects in. And Z is a vector on the coupler solid. Z is rigidly attached to the coupler link, and it goes from this pin joint to P1, and so we have Z right here. All of these letters that I have out here right now are of no consequence yet, but they will be shortly when I move into that position by making that position active. And now here is, I think, the view of my picture that most resembles the picture over here. And let's look at what we have. This is the 4-bar. The green thing is the 4-bar now. Yellow line here, red line here is the triangle now. Blue is the airfoil now in this new position. And the airfoil has moved, the point on the airfoil has moved from location P1 to P2. So we have everything now, but we also have hints of the position 1. Here is our link W in position 1, Z in position 1. Here's the right-hand side of the mechanism, W and Z in position 1. Dotted line for the essence of the coupler link. You can see the triangle remaining in position 1. You can see the airfoil remaining in position 1. So this is an attempt to draw the machine in 2 different positions and match this figure. Now, what is this figure all about? This was our input link in position 1. This is where the input link moved to in position 2. There is a vector that goes from this dot to that dot, okay, attached to this link, okay, and this vector gets a new name from this vector because this vector is different than this vector. This is the edge of the coupler triangle in position 1. It was labeled Z. but that edge moved with the triangle. Can you see the triangle right here? That edge of the triangle in this position has moved to this position. And because the vector that was attached to that edge is in a new location, we're going to give that vector a new name. We have the machine, the 4-bar in position 1. We have the 4-bar in position 2. Now I want to focus on these red lines. This is the W vector in position 1. This is the Z vector in position 1. Here's P1 and P2. A delta vector lets us transit from P1 to P2. Notice the delta vector right here, transiting from P1. Let's assume that J is 2. So delta transits from P1 to P2. Okay, and then we have the Z vector in the second position. And in this figure, we have the Z vector in the second position. And then we have the W vector in the second position. And we have a vector loop. And that vector loop will give us our governing equation. And that loop is travel through the W vector plus Z plus delta 2 minus this Z thing minus this W thing. It shows up better on the author's figure because he has vector arrows. W plus Z plus delta minus the new Z minus the new W is a vector loop that closes. And I would say no matter how the machine moves, let me get to where I can move it easily. Bear with me for just a second. Oops. I sure don't want that. That messes up everything. Okay, I think that's better. Let's drop this down a touch. I hit the wrong keys. Okay, and I need to move this one up a touch. You can't see what I'm clicking on, but I'm grabbing my controls. Okay. So we have a 4-bar that moves the coupler, which has interesting shape, that has been welded through an object from P1, arriving at P2, sort of matching this diagram, giving us our governing equation, and then finally it arrives in a new position called the third position, P3. Let me get her there. I guess that was all the way. No, it wasn't quite all the way to the right. That's not quite what I wanted. Okay. It has arrived at P3. And do you see our vector loop has remained closed the entire time? Okay. And the only difference between our first loop and our second loop is we have a much longer delta vector that we're going to call delta 3 because it takes us from P1 to P3. But our vector loop remained closed the entire time, which means our loop equation was true the entire time. W plus C plus delta minus funny Z minus funny W equals vector loop 0. Now, one thing I want to talk about is, and let's move this back out of the way. You can't see it again. Let's maybe go into this position. Okay, is why in this position here is this new Z term written the way it is? Okay, so let's look at what the Z vector is. Z is a vector on the edge of a rigid body triangle. This is Z in the first position. This is Z on the edge of the moved rigid body triangle. So the question is, how did the Z vector change in going from position 1 to position 2? Did that vector change length? And the answer is no, it could not have. Why? Because it is a Z vector on the edge of a rigid body. Rigid bodies don't change lengths. So how did that vector change? Well, it merely went through a rotation. How do we express rotations using complex vectors or complex numbers to represent 2D vectors, we express rotation as an e to the I theta kind of mathematics. And so by calling this z times e to the I alpha, we're admitting that this vector and this vector, both having the same original vector z, that this is a rotated version of that. And that's what the e to the I alpha operator does. If you recall our discussion in class last time, we said that a synthesis problem needs a three-position synthesis problem must have three positions, a P1, a P2, and a P3. We also said it must have two angle changes, and we said we would denote those angle changes, not absolute angles, but changes. From position 1 to 2, we said we'd call that alpha 2. And from position 1 to position 3, we said we'd call that alpha 3. If you look at the body that I'm intending to move, you can see that this line, as compared to that line, has had an angle change. If this blue body is welded to the triangle, and let's go back to position 1 for just a second. That would be here. Okay, the blue body welded to the triangle, then this angle right here, of course, should remain a constant, and so should all the angles within the triangle. And however much this line right here changes angle as the machine moves, this line should change the angle by the same amount, and so should that, and so should that. So if I go to a slight change, I would argue that this angle change right here must equal the red angle change, which must equal the yellow angle change, which must equal the green angle change. That all of those angle changes are equal. So if we're going to call the change in angle of the body we're carrying alpha, and in particular when we move from position 1 to 2, if we're going to call it alpha 2, then when we move the entire mechanism from position 1 to 2, we're going to say that this z vector has changed its angle through a value alpha, and in fact we would probably call it an alpha 2 is a better name in this place. So that's the justification for naming this e to the I alpha 2 as shown here, except j instead of 2. Now, is this link rigidly connected to the plate? The answer is no. It's connected by a pin joint. Therefore, when the machine moves, must this link change angle by the same amount that this link changes angle? And the answer is no. Since they're connected by a pin joint, this angle right here can be different. So as the machine moves from position 1, red line, to position 2, green line, for this lower link, how does the new vector relate to the old vector? Well, we still have the vector superimposed on a rigid link from position 1 to position 2, from 1 to 2. So that vector cannot grow in length, but that vector can have an angle change, and that angle change being different than the angle change up top, we're going to give it a different name, and so we're going to call that angle change a beta. And in particular, when going from position 1 to position 2, we're going to declare this angle right here between this red line and green line, we're going to declare that as beta 2. Okay, therefore our loop equation to denote traveling from position 1 to position 2 of the machine would be a w plus z plus delta 2, which is the difference between P1 and P2, minus z2 e to the I alpha 2 minus w e to the I beta 2. So let's go ahead and modify our governing equation and put 2's in there. Okay, and this is our equation in position 2 of the machine. What would it look like in position 3 of the machine? Let's move to position 3. And I don't have the diagram fully labeled, okay, because I haven't labeled these things. But what the equation will look like is I'm going to grab it. I'm going to move it out of the way just a second to copy it. Copy it. Paste it. Let's move it over a little bit. Put them both back. Move them up a little bit if I can. Uh-oh, MathCAD application stopped working. Well, that's a bummer, but here's the deal. I see if I can get that out of the way.